Our next topic is heat exchanger. First question is, two concentric cylinder is there and counterflow is taking place. So we have to find effectiveness. So from this diagram, it is given that the hot fluid is passing through the outside surface and inlet temperature of hot fluid is 100 degrees Celsius, outlet is 50 degrees Celsius, and for cold fluid inlet is 25 and outlet is 45 degrees Celsius. So we have drawn this simple diagram to understand the question better. So inlet of hot fluid is 100 degrees Celsius and outlet is 50 degrees Celsius. Then for cold fluid inlet is 25 degrees Celsius and outlet is 45 degrees Celsius. Cp is given to us 2130 joule per kg Kelvin for hot fluid and mass flow rate is 1 kg per second. And for this is our hot fluid and this is our cold fluid. For cold fluid Cp is given as 4178 joule per kg Kelvin and mass flow rate is 1.5 kilojoule per second. So we know that effectiveness is equal to actual Q by Q max. So basically actual Q is mCp into change in temperature of hot side or cold side, whichever side we want to take. So in this case, what we usually do is to calculate our Q actual, we see that m dot Cp minimum. We take minimum of m dot Cp, like whichever fluid, even if hot fluid or cold fluid, whichever fluid gives minimum m dot Cp, we take that into temperature difference of the fluid which is giving minimum m dot Cp. Like in this case, our hot fluid is giving us m dot Cp minimum, which is 1 into 2130. So we are taking its multiplication with temperature difference of hot fluid. And to calculate Q max, we have to multiply m dot Cp of m dot Cp minimum, which is again our hot fluid, and maximum temperature difference. Like between the 4 inlet and outlet, the maximum temperature difference would be Thi minus Tci. So this would give us Q max. So our efficiency would be Q actual by Q maximum, which comes out to be 0.66. Next we have counter flow heat exchanger. Inlet flow temperature is given to us and ratio of capacity, rate of hot and cold fluid is given to us 1. We have to calculate LMTD for heat exchanger. Efficiency is given as 0.7. So let's understand with the diagram. So there are two ends, N1 and 2. Inlet for hot fluid is 170 degrees Celsius. Inlet for cold fluid is 30 degrees Celsius. And we don't know exit temperature for hot and cold fluid. This is a counter current flow diagram. So see, the ratio of capacity is given to us, which is basically mCp of cold fluid by mCp of hot fluid, and it is given as 1. So if our ratio of capacity is 1, then LMTD would be basically delta T of end 1 or delta T of end 2. Temperature difference of end 1 or temperature difference of end 2. So efficiency we know is TCE minus TCI delta upon THI minus TCI is equal to THI upon minus THE upon THI minus TCI. So this is the formula of our efficiency. Efficiency is given as 0.7, and we know TCI, inlet temperature of cold fluid, and inlet temperature of hot fluid. So putting in the values, we get our exit temperature of cold fluid, and from there we can calculate our temperature difference for end 1. So which comes out to be, TC comes out to be 128, and temperature difference for end 1 comes out to be 42 degrees Celsius, which is nothing but our LMTD. Next we have counter flow double pipe heat exchanger is it is a superheated stream is used to heat water at rate is given as m is equal to 10,000 kilogram per hour. Steam enter at 180 degrees Celsius and leaves at 130 degrees Celsius. Water inlet is 30 degrees Celsius, outlet is 80 degrees Celsius. H is given as 814 watt per meter degree Celsius. We have to find heat transfer area. So Cp of water we know 4186 joule per kg Kelvin. This is not given in question, but specific heat of water we know and we are going to use it further in the question. So the simplified diagram is for counter flow N1 and N2. Hot fluid inlet 180 degrees Celsius, hot flue exit 130 degrees Celsius, cold flow inlet 30 degrees Celsius, cold flue outlet 80 degrees Celsius. So temperature difference for N1 would be 100 degrees Celsius and temperature difference for N2 would be 100 degrees Celsius. So both T1 and T2 is temperature difference for N1 and N2 is equal. So which means this is equal to LMTT. Both of these, when temperature difference between N1 and N2 is equal, then it would be equal to LMTT and it comes out to be 100 degrees Celsius. So Q we know is HA into LMTT, which is equal to MCP delta T of hot fluid. So putting in the values, H we know 814 given in question, area we have to calculate, LMTT is 100, M is given to us 10,000 and this is given in hours, kg per hour. So to convert it into kg per second, we would divide it by 3600 and temperature delta Cp is given Cp we know of Cp of water 4186 and delta Th temperature difference for hot fluid, which is 180 minus 130 is 50, and putting all the values we can calculate our area. Next question, it is given to us, all this information is given to us. Counter flow, we can see from the diagram it is counter flow and hot fluid inlet we don't know, but hot fluid exit we know is at 300 Kelvin and cold fluid inlet is 280 Kelvin. Cold fluid exit we don't know. Then mass flow rate for hot fluid is 0.4 kg per second and Cp is 1000. For our cold air, Cp is 1000 and mass flow rate is 0.4. So as you can see, m dot Cp for both of these are given as same. Okay, area is given to us 20 meter square. Overall heat transfer coefficient is U is 20 watt per meter square Kelvin. We have to find us our TCE, temperature of cold fluid exit. So as we said that m dot Cp of both hot and cold air is equal. So which means LMTD would be equal to temperature difference for N1 or temperature difference for N2, which is equal to, like from this end we can see delta T for second end would be 300 minus 280, which is equal to 20 Kelvin. So this would be equal to LMTD. Okay, then so this means that temperature difference for this end would also be equal to, because it is temperature difference for N1 is equal to temperature difference for N2. So for N1, 20 Kelvin would be equal to THI minus TCE, which would be equal to 20 Kelvin. So Q we know is equal to UA LMTD. From here we can calculate Q. U is given to us, overall heat transfer coefficient, area is given, LMTD we have calculated, so Q comes out to be 8000 kilowatt, and Q is also equal to MCP of hot fluid into delta T of hot fluid is equal to mCp of cold fluid into delta T of cold fluid. So putting in the values of Q and m dot mCp, mass flow rate, into specific heat, into temperature of cold fluid exit, which we have to find, and cold fluid inlet we know. From here our temperature of cold fluid exits come out to be 300 Kelvin. Next question is counterflow. Again, for hot fluid inlet is given as 120 degrees Celsius and outlet is given as 60 degrees Celsius, and cold inlet is 40 degrees Celsius and cold outlet is 80 degrees Celsius. So temperature difference for end 1 would be 120 minus 80, 40 degrees Celsius. For end 2 would be 60 minus 40, 20 degrees Celsius. And Cp is given as, for hot fluid, 2 kilojoule per Kelvin, and for cold fluid we have our mass flow rate 1.5 kg per second, and Cp is given as 4.2 kilojoule per kg Kelvin. And overall heat transfer coefficient is given to us 400 watt per meter square Kelvin. We have to find area. So we know that Q is equal to UA LMTD. From here we can find our area, which comes out to be Q by U LMTD. So to calculate area we have to find Q, our U is given to us, and LMTD. So Q we know is m dot Cp of cold fluid into delta T of cold fluid. So putting in the values we can get our Q from here. Then for LMTD, for counterflow we know that temperature difference of end 1 minus temperature difference of end 2 upon ln of temperature difference of end 1 by temperature difference of end 2. So putting in the values we get our LMTD is equal to 28.86. Now for area, area is equal to Q by U LMTD. Putting in all the values, our area approximately comes out to be 21.84 meters square. Next we have for parallel flow. What is given to us? This is a parallel flow. The hot fluid is entering at THI is 400 degrees Celsius and leaving at 220 degrees Celsius, and cold fluid is entering at 30 degrees Celsius and leaving at 110 degrees Celsius. So our inlet, both of these are inlets, so inlet temperature difference is 400 minus 50, 350 degrees Celsius, and for exit temperature difference is 220 minus 110 degrees Celsius. Okay, then heat transfer is given to us, which is Q 155,850 kilojoule per hour, and heat transfer coefficient 68 watt per meter square Kelvin, and this is a shell and tube heat exchanger. So we have to find the outside diameter of tube is given to us 70 meter. We have to find length of tube required for heat transfer. So we know how to calculate LMTD, which is temperature difference for inlet minus temperature difference for outlet upon ln of temperature difference for inlet upon temperature difference for outlet, delta Ti minus delta Te upon ln delta Ti by Te. Putting in the values, our LMTD comes out to be 207.43 degrees Celsius. Then to calculate Q is given as HA LMTD. Okay, Q we know 155,850 given to us, and it is in kilojoule per hour. To convert it into second, divided by 3600, which is equal to H given to us 68 into area. Area is pi diameter into length. So pi into diameter into length. Diameter, outside diameter is given 70. Length we have to find, and LMTD we have calculated as 207. So putting in, solving this, we would get our length is equal to 13.95 meter. Next question is, for same temperature, hot fluid inlet and outlet temperatures, parallel flow and counter flow is taking place. Like the inlet temperatures and outlet temperatures are same, and for this parallel flow and counter flow is taking place. So we have to find the area of counter flow upon parallel flow. So in this diagram we can see parallel flow. For parallel flow, inlet hot fluid is 80 degrees Celsius and its exit of hot fluid is 50 degrees Celsius. And for cold fluid, inlet is 10 degrees Celsius, outlet is 25 degrees Celsius. In counter flow, temperatures are same, but the flow is in different directions. So inlet of hot is 80, outlet of hot is 50, and cold is entering from this side. So inlet of cold is 10, outlet of cold is 25. So from here we can find our, for parallel, delta Ti, which is inlet temperature difference, is 70 and outlet temperature difference is 25. And for counter flow, temperature difference for end 1 is 55 and for end 2 is 40. So Q we know is UA LMTD. From here we can calculate our A, which is Q by UA LMTD. So we can say that area of counter flow by area of parallel flow would be equal to, area is inversely proportional to LMTD. So it would be equal to LMTD of parallel flow by LMTD of counter flow. So we have to calculate LMTD of parallel and counter flow. So LMTD for parallel flow would be temperature difference of exit minus temperature difference of inlet upon ln of temperature difference of exit by temperature difference of inlet. Putting in the values, LMTD for parallel would be 43.73, and for counter current, LMTD is temperature difference at end 1 minus temperature difference at end 2 upon ln of temperature difference at end 1 upon temperature difference at end 2, and it comes out to be 47.1. As we have studied earlier as well, if there are same inlet and exit temperature, so LMTD of counter flow is always greater than LMTD of parallel flow. So our area of counter upon parallel would be, area is inversely proportional to LMTD, so area of counter by parallel would be 0.927. Next we have water at a rate of 2.08 kg per second enter parallel flow heat exchanger at 15 degrees Celsius to cool 2.22 kg per second of air at 100 degrees Celsius. H is given as 140 watt per meter Kelvin and area is given as 20 meters square. We have to calculate exit temperature. Cp of water, we know specific heat of water 4.18, specific heat of air 1.055. So inlet hot fluid temperature is 100 degrees Celsius, which is equal to 373 Kelvin, and cold fluid inlet is 15 degrees Celsius equal to 288 Kelvin. Exit of hot fluid and cold fluid is not given to us. So MCP of hot fluid we know we would calculate. So M is given 2.08 into Cp 4.18 comes out to be 2.23, and for cold fluid M is given as 2.22 and Cp is 1.005. For air it comes out to be 8.706. So NTU, we know that NTU is equal to HA by MCP minimum. So MCP minimum is for our water, hot water, which is 2.23. So H we know is 140 given to us. Area we know is 20 given to us. Then MCP minimum we have calculated. From here we get our NTU is 1.254. Effectiveness we know is equal to 1 minus e to the power minus 1 plus c into NTU upon 1 plus c, which is equal to delta T of hot fluid upon delta T maximum. So C we know is MCP of cold fluid by MCP of hot fluid. So we have calculated both of these. So from here we can calculate our C, and we can, in this equation, the value of C, we can put the value of C in this equation here, and NTU we have calculated. So effectiveness comes out to be 0.631, and it is equal to delta TH, temperature difference of hot fluid, THI minus THE, inlet hot fluid minus exit hot fluid, upon T max, that is inlet of hot fluid minus exit of cold fluid. So THE comes out to be 319.365 Kelvin. Next we have question for condensing fluid. So in condensing fluid, THI, hot fluid inlet and exit, remains constant, like hot fluid is entering at 1000 degrees Celsius and leaving at 1000 degrees Celsius, while cold fluid is entering at 200 degrees Celsius and leaving at 500 degrees Celsius. So inlet temperature difference would be THI minus TCI, 800 degrees Celsius, and outlet temperature difference would be 1000 minus 500, would be 500 degrees Celsius. So LMTD would be delta TI, inlet temperature, minus delta TE, exit temperature difference, upon ln delta TI by delta TE. Putting in the values, we can get our LMTD as 638.24 degrees Celsius. Now next question is also based on condensing fluid. Here THI, our inlet hot fluid and exit hot fluid is at same temperature of 30 degrees Celsius, and cold fluid is entering at 15 degrees Celsius and leaving at 20 degrees Celsius. Inlet temperature difference is delta TI is 15 degrees Celsius, and outlet temperature difference delta TE is 30 minus 20, 10 degrees Celsius. U is given to us, overall heat transfer coefficient 1000 watt per meter Kelvin, area is 100 meter square. We have to calculate Q. Q we know is UA LMTD. U is given 1000, area is 100, and LMTD we know is delta TI minus delta TE by ln delta TI by delta TE. Now putting in the values, delta TI being 15, TE being 10 upon ln 15 by 10, we get our Q as 1.234 kilowatt. We get it as 12.34 into 10 to the power 5 watt, and by dividing it by 10 to the power 6, we get it as 1.234 kilowatt, and kilowatt is equal to megawatt.